All right, we're doing chapter 5, which is the second chapter on linear algebra part. So our goal is eventually to find the inverse. The inverse is the matrix equivalent of division, and we need inverses. But we've got to do some other stuff to get to that inverse. And the first thing we need to talk about is something called a determinant. Determinant. The determinant is a scalar. It's not a matrix. It's a scalar. It's one number. And it's a number that is unique to that matrix. So each matrix has a determinant, which is a scalar, unless the matrix doesn't. And you're like, Urgh. So, two things. Thing number one. Remember necessary and sufficient? We talked about this a little bit, and we need to talk about it again. If I am in France, that is sufficient condition for me to be in Europe, but it's not necessary, right? I could be in Spain and be in Europe. But if I know that my friend is in France, I know they're in Europe. Okay? A necessary condition for them to be in Europe is that they're not in the United States. That's necessary. But it's not sufficient because they could be in Brazil. Okay? So necessary is something that has to be true, but generally is not enough in and of itself, not necessarily enough in and of itself to make something, right? Sufficient is something that is by itself sufficient to prove something, but it isn't necessarily necessary. Okay? So if I'm in France, that's sufficient, but it's not necessary. If I'm out of the United States, that's necessary, but it's not sufficient. Most problems we're going to have some necessary condition and some sufficient condition for us to get a determinant. Okay? Or for other things. When we get into optimization, we're going to have necessary and sufficient conditions again. So we're going to see these over and over and over again in different contexts. And it's important that we understand the difference and we can identify it. Yes? Okay. Hopefully we have that, right? Yes? We have it by now? It is necessary to be out of Nevada to be in California, but it's not sufficient. If I'm in LA, that's sufficient to prove I'm in California, but it's not necessary. I could be in San Diego or somewhere else. Okay? Okay, so a couple things to remember beyond this now. One, to have a determinant, we have to be a square matrix. So only square matrices have determinants, which means if we want to do the matrix equivalent of division, we either have to be doing it on matrices that are by themselves square, or we have to do something that turns them into square matrices. Okay? Everybody with me on that? So that's necessary, but it's not sufficient. And the reason it's not sufficient is that the matrix has to be non-singular. Okay? Those two together are necessary and sufficient. Non-singular means it has full column rank. And again, what does that mean? Well, it means that the rows or the columns in the matrix can't be linearly related. So again, if I have this matrix, this row is twice that row. This matrix is singular. It really only has one row. because the second row is twice the first row. The two rows are not independent of each other. It really only has one row. So instead of, if I have this matrix, okay, that has a rank of 2 because it has two independent rows, or two independent columns, same thing, okay, has a rank of 2. This matrix only has a rank of 1 because basically it only has one row. Or if you look at the columns, it only has one column, right? Either way, it doesn't matter. It has a rank of 1 because there's a linear relationship between the two columns or the two rows. Okay? For a determinant to exist, we have to have a non-singular matrix, which means our 2 by 2 has to have a rank of 2. It has to have the same rank. Okay? Now you're saying, well, how do I figure that out? Just sometimes you can just look at it, but there's another way, and we can, in fact, there's 2 other ways. We're going to only do one of the other ways. But the trick here is those two things. To have a determinant, you have to be square and you have to be non-singular. Okay, so now what does this mean? What does this mean? What does this mean? So if I have a matrix A, which is just a 1 by 1, okay, the determinant of that, and for determinant we put the matrix and then we put 2 parallel lines there, 2 straight lines. We don't do the whole, that and that and that and that. We just do 2 straight lines. Okay, that means determinant of A. Well, the determinant of a 1 by 1 is itself. Okay, so the determinant of this is 5. That's pretty boring. Now let's suppose that A is a 2 by 2, just a generic 2 by 2. Do we remember that we have A11 means first row, first column. A12 means first row, A11, right, first row, first column. First row, second column. Second row, first column. Second row, second column. Okay, so what we do to take this determinant is we pick a row or a column. And usually we just pick the first one, but there's reasons why you might want to pick another one. Doesn't really matter. We pick a row. So let's pick row 1. Okay? Yes? And we take the number that's in row 1. Then we eliminate the rest of that row and the rest of the column. And we take what's left and we multiply it times that A11. Okay? Is that exciting? All right. Now, why? So let's look at A11. 1 plus 1 is 2. If I look at A12 here, 1 plus 2 is, 3. This is even, and that's odd. Okay? If it's even, I'm going to leave the sign just the way it is. I'm just going to leave it like that. When it's odd, I'm going to put a minus sign in front of it. So now I'm going to take A12, yes, and I'm going to eliminate the rest of that row and the rest of that column, and I'm going to write A21 in here. Okay? You're like, we'll do some examples here in a second. Should make sense. That is the determinant. Okay? That equals the determinant of the matrix A. All right, you're like, so let's try this. Determinant of A, if A is 2, 3, 4, minus 1, equals, take the 2, eliminate the row and the column, and multiply it times minus 1. Then take the 3, put a minus sign in and a 3, because it's 1, 2. Eliminate the row, eliminate the column, multiply that times 4. Yes? And I get minus 2 minus 12 equals minus 14. And that minus 14 is the determinant of the matrix A. Exciting? Okay, you're like, all right. This is a really simple thing to do. Okay? So if this is A, determinant A would be 4 times 3 minus 5 times 1. Okay? I take the 4. I eliminate the row and the column. I have a 3. I take the 5. I eliminate the row and the column, and I have a 1. Multiply that out is 12 minus 5 equals 7. Okay? 4, 5, 1, 3. If that's A, it's 4 times 3 minus 5 times 1 is 12 plus 5, right? Why did I do that one twice? Don't even. Just, yeah, don't even, because I had that and then I changed the bottom. So if that's that, determinant of A, right? Determinant of A is going to be 4 times 3 minus 5 times 0 equals 12. Now, he said, let's go back and do this one. We said this one doesn't have rank, right? This is singular. It's a 2 by 2 with a rank of 1. What's the determinant of this? Well, the answer is 2 times 8 minus 4 times 4 is 0. Oh my. Something exciting happened. Oh my. So there's a way to go through the matrix and figure out whether it's singular or not. And it's complicated. Okay? It's complicated. It involves these things called elementary row operations. And you set the whole thing up there. Okay? There's an easier way to tell if a matrix is singular, and that's just to go ahead and calculate the determinant. The determinant of a singular matrix is always going to be 0. Okay? So we can't get ourselves in a bad position where we're trying to solve a problem without realizing that the matrix is singular. If it's singular, as soon as we do the determinant's going to be 0, and we go, oh, singular. Okay, now you're also saying to yourself, why the heck does this matter to me? I don't care. Well, you care for 2 reasons. One is we need to find inverses, and determinants are finding inverses. The other is that maybe you've taken an econometrics class. Maybe you took 262 or 441 and you've taken an econometrics class. And they told you, hey, multicollinearity is bad. And you're like, okay, I get that. Why is it really bad? Well, if you have perfect multicollinearity in your data set, your data is a singular matrix. Ooh. Now you're like, wait, well, no, I'm not going there. I do not want to go there. But that's the reality. Okay? It does bad things. If you have partial, strong multicollinearity but not perfect multicollinearity, then you're going to get bad outcome, and there's all the econometric stuff, and I'm not going to go into that. But if you have perfect multicollinearity in your data set, the regression will not calculate. And the reason it won't calculate is because the determinant of your data set is going to be 0. Ooh, yeah! Math is everywhere. And we don't explain these things to you in 261 or 441 maybe, because then we'd have to make sure you knew linear algebra, but now you know. So now you know secret stuff. If you're taking 441 in the fall maybe, and you haven't taken it yet, or you're taking graduate econometrics, and you start talking about talking about multicollinearity, and your professor says it's bad, and you go, is that because the data is singular? You could really impress your, who's ever teaching that class, because you know cool stuff. Cool stuff. Now, he said, we need to get complexical. Okay? The way we solve this is something called a Laplace. Yes? Laplace. That's the guy's name who invented all of this. Okay? It's a Laplace expansion. So let's suppose we have a 3 by 3. Well, a 3 by 3 looks like this. Okay? And again, those are A's. Those are not 9s. Those are A's. 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 All right? Everybody with me on this? Again, we're going to pick one row or one column, and we're going to do an expansion on that row. So we're going to start out, 1, 1 adds up to 2, which is positive, so we just write 1, 1. Then we eliminate the row and eliminate the column. Now, I have a matrix. So I'm going to multiply that A11 not times some number from my matrix. I'm going to multiply it times the determinant of that matrix. And then I'm going to subtract A13. And again, I'm going to eliminate the row and eliminate the column. And I'm going to build a matrix. I'm going to take A21, A31, A23, A33, and I'm going to build a matrix. Okay? And then I'm going to take this third number. Oh, that's a 2, A12. Because 1 plus 2 equals 3. Now I'm going to add A13. 1 plus 3 equals 4. That's even, so there's a plus sign. Now I delete the row and the column, and I get A21, A22, A31, A32. And I solve that, and you're like, yeah, that looks like so much fun. I'm going to solve this, baby. I'm going to solve it. And that's going to be the determinant of A. Okay? Yeah. Let's try one of those.